Good afternoon, everyone. Am I audible?
Yes,
Okay. So today is the fourth interaction session on structural vibration. So my name is Devashish Panda. I am a Prime Minister Research Fellow at IIT Guwahati. So during this semester, January-April 2025, I have been allocated to this course, Structural Vibration, as Prime Minister Research Fellow TA. So every Saturday from 3 to 5 p.m., we conduct a interaction session where generally we go through the concepts of the current week, then we solve different kind of problems on pen and paper, and we do some MATLAB example. And after each recording you will get the link of the recording session, link to the solve assignment problem and notes, and also the MATLAB scripts. So today we will go through the force vibration under step and pulse excitation, how to solve you know different responses due to arbitrary loading, and the concept of Duhamel integral. Then we will move to the force vibration in frequency domain part, where we will learn the Fourier series transformation and also the concept of the frequency response function. And then we will conclude with the Parseval theorem. Okay, so then first we will go through these concepts, and then we will solve different kind of problems which will be useful for your current week assignments, uh, to solve the current week assignments problems, and you can easily correlate with that. Okay, so during the last interaction session, we went through the force vibration and force vibration for damped and undamped case for harmonic excitations, right? Where we have used an sinusoidal harmonic load or harmonic load as a form of P naught sine omega bar t, where P naught was the amplitude of this force and omega bar was the forcing frequency. And we have solved, and we have seen that the final solution contained a particular integral part and a complementary part. The complementary part due to the inherent properties of the system, and the particular integral part generally influenced by the application of load. And finally, we have this final solution in the form of this, where this first part represents the transient response and second part represents the steady state response. So during the last interaction session, step by step, we have done the derivation. Go and watch the video. You that concept will get clear. And then we have seen the concept of the steady state response. After transient response died out, only the steady state response will be there, and we actually interested in the steady state response. So the steady state response we can express in the form of like that: ut or xt is equals to u naught sine omega t minus phi, omega bar t minus phi. Okay, where u naught is nothing but the dynamic displacement, right? And u naught st was the, recall, just we have already solved these things during the last interaction sessions. So ust was the nothing but the static response, and from where we have sorry, we have the concept of the dynamic response factor RD, which is nothing but the ratio of the dynamic deformation to the static deformation, and we have generated a closed form solution for this, and we have discussed all these things during the last interaction session. So basically, during the last interaction session, we have solved forced vibration under harmonic excitation, and we have seen that how the responses will vary and vary with time, and what will be the steady state response, what will be the transient response, and all these things. So we have covered these things. So today actually we will see force vibration under step and pulse excitation. So in previous day we have considered that f of t is a form of a harmonic force like p naught sine omega bar t, or you can use cos function also. We will get the solution subsequently. So today we will see how the response will vary when a step or pulse excitation will come. Now, what we call the step and pulse excitation or pulse forces or impulse forces, I will define it uh, during the courses. So first, like Let's consider a scenario where a constant force. Let's first consider this scenario where a constant force P is applied on a single of spring mass damper system, where obviously this damping device is designed or modeled as per the viscous damping theory. So obviously, if we formulate the equation of motion, so the equation of motion will look like this mx double dot. Here I am considering x is my degree of freedom. So generally in the during the interaction session, sometimes I use x of t for the responses, and sometimes I use u of t. Both are same. You can use any of them to maintain the consistency of this problem. Okay. So obviously, the equation of motion is formulated. So this is the equation of motion of the system under this P force. Now, if I want to solve it, obviously it's a second order non-homogeneous equation. So obviously it will contain a complementary part, and the complementary part will nothing but its damped free vibration case. So directly we can already we have solved it that for the damped vibration case. So damped free vibration case, what will be the solution? So it's nothing but e to the power zeta omega n t a cos omega dt plus b sin omega dt. As damping is present, that's why omega d. So omega d also we know omega d is nothing but omega n under root of 1 minus zeta square. Okay, so this is my complementary part of this equation, right? What will be the particular integral? So already I have mentioned or discussed that particular integral part influenced by the load acting on this system. So here only a static force, constant force is acting on this system. So obviously the particular integral part will be p naught by k. So now if I formulate the complete equation, so the complete equation or the complete solution for this equation will look like this. Xt is equals to nothing but this is my complementary part which comes from this free responses. So e to the power zeta omega n t, zeta is nothing but the damping ratio, omega n is the free natural frequency or undamped natural frequency of the system, or you can say the natural frequency of the system. Natural frequency, already you have defined natural frequency, the frequency at which the system vibrates freely without any influence of the external loading. Then this p naught by k will be there. Okay, now here we have two constants a and b. So obviously the constants a and b can be found out using the initial condition. So if we impose the initial condition that at t equals to 0, my initial displacement is x naught and the initial velocity is x dot naught. Okay, here you should remember that x naught and x dot naught is not the derivative of this x dot. It's the initial displacement x dot. You can consider initial displacement or displacement at t equals to 0 if we consider, and this is the initial velocity, not the differentiation of these things. Initial velocity, or we can define it instead of this x dot naught, we can define it v naught also. Okay. So if we solve this, so first we will impose the initial condition that at t equals to 0 my displacement is x naught. So obviously put all these things in equation number 2. Say I name it equation number 2. In equation number 2 I will get that x naught is equals to a plus p by k. So obviously here from here I can get the a is equals to nothing but x naught minus p by k. Now differentiate equation number 2 with respect to t and impose the second initial conditions. So what we will get? We will get like this: x dot naught, the initial velocity, is equals to minus zeta omega n a plus omega d b. So obviously we have found out the value of a. Substitute the value of a here and solve for b. So we will get the b is equals to nothing but this. Straightforward derivation. Now if we want to complete the solution, so the complete solution will look like this. Xt is nothing but e to the power zeta omega n t. Then a, already we have found out the value of a, cos omega dt plus b. This is the value of b, sin omega dt plus p by k. Okay, so we have now the solution or the response of a system under a constant loading is applied on the structure, and the intensity or the magnitude of loading is nothing but p. So if we have this kind of conditions, then the final response will be like this. Now why I am doing this? Because ultimately what I am doing now will the conclusion will lead to a important concept which we call the initial response of a structure. So up to this clear? Now if we rewrite the equation little differently, like here uh, the part f naught by k, I have just written it like f naught by, we know omega is equals to nothing but of root over k by m. So in the form of m omega square, I have written it down. Now I am applying the initial conditions, that the initial displacement also zero, initial velocity is also zero. Okay, I am not considering any initial conditions. That means the zero initial conditions I am now considering or taking into account. So if I have the zero initial condition, now from this equation I will find out that a is equals to nothing but minus f naught by m omega n square, and differentiate this equation number 2 and impose the second initial condition, that the initial velocity will be 0. So b we will be find out in the terms of this minus f naught by k zeta divided by under root of 1 minus zeta square. So the final complete solution will be f naught by k 1 minus e to the power zeta omega n t cos omega dt plus zeta by under root of 1 minus zeta square sine omega dt. So in the form of this equation, we will get the solutions. Now, here was the complete solution. Solution of what? Solution of a single degree of freedom system, single degree of spring mass damper system subjected to a constant force applying onto it, and we are imposing zero initial condition, right? So here we have the spring mass damper system, and here one p load is acting on the system, and the mass can move in this direction. So this is my degree of freedom for this system. So k c. So for this system, if we impose the initial conditions, zero initial conditions, that means at t is equals to 0, my initial velocity, initial displacement is also 0, and the initial velocity term is also 0. So how this response will look like, the final solution will look like this. Now if all these parameters are provided, and if in a question it is asked that okay, all is SDOF system or spring mass damper system is subjected to P. The intensity of P is also given. Zero initial condition is given. What will be the response at T is equals to, say for example, at T is equals to 2 seconds. So we can easily calculate the responses. Now here also we can have two cases. First case, so it's a important thing, like if you know the expression and this kind of question asked, then you can easily solve this question using this final solution form. Now here also we have two cases. First case, the undamped case, where zeta is equals to 0. Now put zeta is equals to 0 in equation number 4. So what will we get? We will get only xt is equals to, just put zeta is equals to 0, you will have the response or the undamped response is like this: f naught by k 1 minus cos omega nt. Now obviously the omega d become omega n, because we know omega d is equals to omega n under root of 1 minus zeta square, and zeta tends to 0. That means undamped case. So damped natural frequency will become the undamped natural frequency. That means the natural frequency of the system. Now if this cos omega nt, this part here also two cases will be there. So that means This will be the response. X of t is equals to f naught by k 1 minus cos omega in t. That means the response will have a mean of f naught by k. It will not oscillate at zero mean. It will oscillate at the mean of the static deformation f naught by k. So what will be the maximum value or the bounded value for this response? So when cos this part cos omega nt, this part will be 1, then the response will be 0, and that will be 1 here at 0 position. So obviously it will start from here. Then when this part cos omega nt will become minus 1, when it will become minus 1, when it will reach to 180 degree out of phase. So for that case, we will get that xt, the dynamic response, is nothing but 2 f naught by k. Dynamic response will be 2 f naught by k. So this response for the undamped case, this response will be bounded by 2 f naught by k magnitude value. On the other hand, when we have seen that we solved for undamped force vibration case under harmonic excitation, we have seen that the response get unbounded, but here this response will be bounded by 2 f naught by k. Now for these scenarios, what will be the dynamic magnification factor or rd? So rd, we know it's nothing but the ratio of the dynamic displacement xt divided by the static deflection x st. So here for this case, the RD value will be xt is nothing but 2 f naught by k, and xst is nothing but f naught by k. So the value will be 2. So this type of question also can be formulated like one single spring mass damper system is provided, and for example, they have said consider the undamped case where zeta is equals to 0, and tell me what will be the mean of the response. So obviously f naught by k. What will be the bounded value of the response? Obviously 2 f naught by k. Already you have seen. What will be the dynamic magnification factor for this case? 2. So this kind of problem also can be formulated. Okay. Now for the second case where the damping will be present. So for you know harmonic excitation case also, we have seen that the response will decay, and this response will follow, the decay response will follow the envelope of e to the power minus zeta omega n t. Now for this case, the response will be, the mean response will be f naught by k, not the mean response will start from the 0, because here already my static component is there. Okay, and this also bounded by the maximum value, also bounded by 2 f naught by k, and as damping will be present, this response will follow this envelope and will subsequently reach to the steady state responses. So what we have discussed till now, if we revisit, so we have a system here, spring mass damper system, where a constant force p naught is applying, and for the zero initial condition we have solved the responses, and this is the complete solution for it. P, magnitude of load acting. And here we have seen the two cases. Okay, undamped case will be there, and we have discussed different kind of parameters, like the mean will be f naught by k, this response will be bounded by 2 f naught by k, the magnification factor will be 2, and for the damped case already we have seen. Okay, so the maximum response will be bounded by 2 f naught by k, and this will follow an envelope of e to the power zeta omega n t. Okay, now what I said, that this will lead to a final conclusion. So now we have the case when the magnitude of p become 1. That means that unit magnitude of constant force is acting with the zero initial condition. So what will happen? The response. So this was the final response with initial conditions. Now zero initial conditions we have solved here. So that was the final turn. Xt is equals to f naught by k 1 minus zeta omega nt cos omega dt plus zeta by under root of 1 minus zeta square sine omega dt. Now here if we put p is equals to 1, we will get x of t is equals to nothing but 1 by k in bracket 1 minus e to the power zeta omega nt cos omega dt plus zeta by 1 minus zeta square under root omega dt. So if we simplify, our xt will become this. Now this response due to, you know, unit force acting on the system with zero initial condition, this type of responses for a single degree of freedom system, we call it initial response of the system. That means initial response we will have when a single degree of freedom system or spring mass damper system is acting or acted by a unit constant force with zero initial conditions. So obviously now this kind of if so unit magnitude of force, that means the force we can express like this. Say this is the force, this is my system, single degree of freedom system or spring mass damper system is subjected to force ft, and ft is denoted by this. That means the value of ft, so if we consider that ft is a function of u, then what we will see that okay, the value when t is less than ta, the value will be 0, and when t greater than ta we will get a value of 1, and at the center point we will have the average of these two half. So if my system is subjected to this kind of load, and this load is called the Hipside step function, that means I will discuss what is Hipside step function. So this kind of load we can easily find out what will be my response of the system, and that is nothing but the initial response of the system, and that actually we have derived. Okay, the form will be like this: 1 by k to the power zeta omega nt cos omega dt zeta by 1 minus zeta square sine omega dt, right? So now we can define what we call the initial response of a system. So if a SDOF system is subjected to a Hipside step function, in that case the response whatever will be produced, we call it the initial response of the system. So we have started from here and we have seen different cases, and we conclude that okay, if a system, a spring mass damper system is subjected to some unit load over the time, then this kind of system we, or this kind of responses we call initial response of the system. Now this initial response will also lead to another important conclusions that we call the impulse response function. So what I said, now we are in a position to define the Hipside step function. So Hipside step function is a type of function here, like from the picture you can see, uh, if the magnitude of u of t will be always 0 when t less than 0, and u of t will be 1 when t greater than 0. So this kind of function or this kind of forcing function we call Hipside step function. That means Hipside step function have the magnitude of the force is equals to 1. Okay. Now from the Hipside step function we can also derive one more function we call the direct delta function. How? Say for example, here we have a Hipside step function, this, and this is defined by u of t. Obviously t less than equals to 0 it will not have any kind of values, and t greater than equals to 0 it will have a constant value 1, magnitude of 1 only. Okay, now if I want to you know uh, resolve it into two parts, so first I can have this part, of constant magnitude 1, and this part also the constant magnitude of 1, but this force is starting from the TA. That means when T is less than TA, the force value will be 0. When T is greater than TA, the value will take 1. Now, if I considered, okay, the magnitude is F, so for now F, so F of T, from this 2 we can write it down that f u of t minus f u t minus ta, because this function starting from ta, so obviously this u will take from the t minus ta part. Now, so what we left with, so we will left with t f and this kind of function, say here this is the ta. Now, when this ta tends to 0, that means it will come here, ta tends to 0 and this f tends to 1. That means this f tends to 1 and ta tends to 0. Then we call the function direct delta function. That means this function only have the value at origin, or if we have a shifted direct delta function, so where say for example t is equals to ta, we will can have the direct delta function at t, either on origin or t. So the most important property of direct delta function is if you integrate the direct delta function over the domain of its, you will get only one, because it has only one value. And if we make the derivative of the Hillside step function with respect to time, we will get the direct delta function. Direct delta function is nothing but it's a unit impulse at either it can be at origin or it can be at different time instances, but it will have only one value at that point. So if obviously if you integrate it over the domain, you will get only one. So here from here we can have the concept like, okay, from the Hillside step function, if we derive if we make the first derivative of the Hillside step function, we will get a function which we call the impulse response direct delta function. And the direct delta function is very important. We will see why direct delta function is very important rather than the Hillside step function. So here there are the concept, okay, if we have the Hillside step, if a Hillside step function means the forcing value will be 1, and if we start the value from here, so obviously for the Hillside step function the value will be always 1. Say this also I can represent at Hillside step function ta, say this is my u of t and this is the value will be 1. That means the Hillside step function u is defined at t minus ta, so obviously the value will be 1 when t greater than ta. That means for the Hillside step function, the constant value, the magnitude of force will be 1. And obviously, if we derive or make the first derivative with respect to time, we will get a function we call the direct delta function. Okay. Now we can define the impact load or impulses. So impulses is nothing but kind of forces which acting for a very short duration of time and whose magnitude is large. So here if we denote, this is ft and this is t, and one in very short duration of time this is acting on it, say for example tau c, this is tau c and this is my value of f. So impulse or impact load is defined as the load which is acting very short period of time and the magnitude of the force is relatively high, but it actually acting on the system on very short duration of time. That means your tau c tends to be 0. That means we will have say similar kind of like this kind of responses suddenly occur and then it diminishes. So this kind of load we can call the impact or the impulse. That means impulse is nothing but the magnitude of force multiplied by time, but the time instance is very small. That means tau c is tends to 0. We call them as the impact load or impact forces or impulses, right? Like here, in this diagram, you can see this is also one kind of impact, but here we can, how we can, express this force, one hip side step function minus this. If we do it, then we will get this kind of functions. We will see when we will solve the problems. Sorry. Now, if we have a hip side step function, what will be the response? Already you have seen that due to the hip side step function, the ultimate or the final response we call the initial response of the system. Here we have already derived it. So g of t, what g of t? This is due to hip side step function. That means due to, and what is the property of hip side step function? The magnitude of force is 1 when t greater than 0. So if we have, now just focus on it, if we have this force, impulse force, this, say for example here, instead of 1 considered, okay, f is my ordinate. So due to 1 uh, magnitude of load, what is the response? Is nothing but gt, the initial response of the system. What will be the response due to this? So I am considering this is equals to this minus this. Obviously if you subtract from here this one, so you will get the force like this, because this is my impact force and I want to derive the responses of, or because of these forces. So if I have only one magnitude, so obviously my response of these two forces, due to these two forces, will nothing but g of t minus g of, that means initial response function at t minus tau c. Obviously now if we have obviously f magnitude of force, so obviously you need to multiply the response with f, because hip side, for the hip side step function the magnitude is 1, but for not for all the cases the magnitude will be 1. Impulse can be different magnitude also, so f. Now what I am doing, I am multiplying it tau c at the denominator and both. So what I am getting, f multiplied by tau c, what is that? F multiplied by tau c is nothing but my impulse I. And what is this part? Gt minus gt minus tau c by tau c is nothing but del g by del t. And what we know just from the previous slide, that del g by del t is nothing but, we call it the impulse response function. Now why we call the impulse response function, or what is the definition of the impulse response function? So if we have a impact of magnitude 1, then the response is called the impulse response function. That means if this I become 1, that means your f into tau c tends to 0, f tends to 1, that means this will become a hip side step function. That means on the system only a constant magnitude of 1 load is acting. So if that kind of scenarios occur, we call the response as the impulse response function. That means the response due to unit impulse, we call the impulse response function. Now how we can get the ht is nothing but, we just need to make the derivation of g, that means initial response with respect to t, and g already we have derived the equation for the initial response of a system. Here is the part. So what do we need to do to get h of t, that means the impulse response function of the system? We need to make first derivation of this gt. Let's do it and see. Okay, so obviously if impulse is coming, the final response we can express like this: x of t is equals to nothing but my impulse. It can be unit impulse, it can be of magnitude f impulse, it can be of magnitude different impulse, multiplied by impulse response function. But impulse response function, the definition of impulse response function is like the response due to unit impulse or unit load. Right. So let's derive the formula of the h of t. So what we need to do? We just need to differentiate the g of t, that means the integral response function, with t. Already g of t we have found out 1 by k, 1 minus e to the power zeta omega n t cos omega dt, zeta by 1 minus zeta square. So make the derivation, you will get the value of gt. So the derivation is done here. H of t finally leads to this equation h of t. It's a simple and straightforward derivation. The steps are already written here, no issue. So finally, the impulse response functions we found out in the form of this. H of t is nothing but 1 minus m omega n square under root of 1 minus zeta square e to the power zeta omega n t, like this. And further, if we simplify it, we know omega n square under root of 1 minus zeta square is nothing but omega d, damped natural frequency. So finally, the impulse response function for a damped system, we have found out that, okay, this is nothing but 1 by m omega d e to the power minus zeta omega n t sine omega d t. So what will be, this is my impulse response function. Now what will be the final response of a system if a system subjected to unit impulse? So it's nothing but your that impulse multiplied by your impulse response function. Now if we have a unit impulse, so obviously the impulse response, that response equals to the impulse response function, and that will become like this. Now so from now, what we have learned, okay, what will be the initial response of a system, what is the impulse response of a system, and how to get it. So impulse response for a damped system is expressed by this. You need to recall this because this is very helpful to solve different kind of problems in time domain. And when we will solve the Duhamel integral, we will see many times we will use that impulse response function, because for when we will go to solve for arbitrary loading, so arbitrary loading part will be uh, divided into different kind of impulses and we will sum them up, right? Now, so what is the final conclusion? If we have a Hipside step function, so the response we call the initial response, and this is denoted by this equation. And if we make the derivation with respect to t, we will get the impulse response function. Already we have derived that two things. Now, why this is important? You will have the flavor here that the derivation is done. If you want to go through the derivation, it's a simple derivation. How this ht is coming as 1 by m omega d e to the power zeta omega nt sine omega dt. This you will find here. Now, what we have seen till now, if the input, if I have a system like this, single DOF spring mass damper system. Now if my ft is harmonics or harmonic loading, we have solved it harmonic. That means on the last lecture we have solved for that ft is equals to some p naught sine omega bar t minus phi. So or cos, it can be cos ft is equals to like p naught, you can solve it for that also, omega bar t minus phi. So if we have the harmonic excitations as a input, so obviously we have the output in the form of this, like it's also harmonic because cos and sine term was there. Now if we have a input u of t as a Hipside step function, like this kind of function, one, this is f of t and t. So obviously you have seen that this we call the Hipside step function. The output will be the initial response g of t, what we have just derived, right? Now if we have the direct delta function as a input, if we have the direct delta function as a input, then we have the impulse response function as an output, because the direct delta function will act as the impulse load at the origin or at t is equals to tau. So this is few concepts you need to recall, which kind of inputs If we provide harmonic force as an input, we will get some harmonics as output. If we provide Hepside step function as an input, we will get the initial response. If we provide the direct delta function as an input, we will get the output as a impulse response function. Now, few questions may come from here, like the Hepside step function can be defined by, tell me. I've already discussed. So you tell me which option will be correct. Bob, tell me. Hepside step function, which will be correct?
That should be C.
Yeah, great. That will be C, because it will only the value if I draw it like this. So it's 0, this my ordinate, this my f of t, and the value of 1. That means obviously this, if I denote it u of t instead of f of t, so obviously u of t minus a will be 0 when this part t less than or equals to a. So this is a, denoted by a here. As per your question, this is a. So when t is less than a, the value will be 0. When t is greater than 1, the value will be 1. So obviously the C option will be the correct option, right? So here, select the correct option about the Hepside step function and the direct delta function. So first thing, if we differentiate the Hepside step function with respect to time, we will get direct delta function. We have just derived it. And one more property I have said about the direct delta function, that if you integrate the direct delta function over the domain, you will get what? You will get 1. That means which one will be correct answers? Option number A and option number D. Right? Yeah or not?
Yes, yes.
Yeah. Now, here is the case 2. Case 2 I will explain later, like how to solve it. Nothing but we will solve few minutes later. It's a simple kind of problem, like this kind of force. Okay, let me explain. This kind of force is acting. The value of force when that t is less than tc, it has a value of f, and when that t greater than tc, it has a value 0. So obviously we will have two equation of motion. First equation of motion, x double dot plus here like x double dot plus c x dot plus kx. First part will be f by f. F. Now just rewrite it and divide it by m. You will get like mx double dot. So if we divide it by m and simplify it, you will get c by m is equals to nothing but twice zeta omega n, and k by m is nothing but omega n square. So first part, if you solve the first part, you will get this xt is equals to nothing but f naught by k, the initial response. We have just solved this. Now here at tc, what we will get, that will provide the initial condition for the second case. So obviously first case is the initial response of the system. From that system already we have solved for the constant loading, and we have seen that this will be the system response up to the tc. And here at tc, what will be the x and x dot naught, the velocity and acceleration, that will be the initial condition for this rest of the part, because after this also the vibration will continue. So for the part b, it's nothing but the damped free vibration case, because force is diminishes, but still due to the initial condition at here t is equals to tau c, the system will keep on vibrating for some times. So obviously for the part b, we will have the solution for the damped force vibration case, and the damped force vibration case solution already we have solved. Xt is equals to zeta omega n t, a cos omega n and dt. So the final response actually will look like this. For the first part, it will already I have shown this curve, like it will vibrate with the mean f naught by k, and for the later part it will come back to the zero initial condition and zero mean position, and it will keep vibrating. Like just recall, already we have solved it few times back initially, and we have discussed it elaborately about this, how we are getting these responses and all these things here. Mhm. Here this part, only the first part was there because a constant load was acting there. constant load for magnitude of P and for the whole duration of time. But for this case 2, why I have added this case, because here after time Tc the load become 0. But we will have some responses due to the initial conditions from here. So similar kind of problem, but for the second part we need to solve, and we have seen that this kind of responses we will have. Okay, this problem actually why I was telling that okay we will discuss it later, because we will solve using the MATLAB, different kind of problems using MATLAB, how the responses will look, what will be the value, how to solve them using Duhamel integral, and how to get the answers easily. I will show you all these things during the MATLAB. So now so till now we have done what will be the responses due to Hillside step function, direct delta function. That means we have the idea about the initial response, and also we have the idea about the impulse response functions. Now, if some general arbitrary loading is coming on the system, how to solve the system using these concepts, and how these concepts will finally lead to that Duhamel integral part. So now, say, just imagine like we have a system, single mass DOF system, single spring mass DOF system. We have M, C, and this one is your K. And one general arbitrary loading is acting on it, F of t. And F of t is represented by this arbitrary kind of loading. Okay. So how to solve it? So look at the loading. If I, slice the loading like this, so the each slice will represent what? Each slice will represent one impulse. Yes or no? Because we know impulse is nothing but your magnitude of force multiplied by the duration of time. So at each slices, if I make the slices of this general loading, so each of the slices will represent the impulses. Now let's consider one slice here. Okay, at t is equals to tau, and the width of this or its dt apart. So obviously, what will be the response due to this small slice? What will be the response due to this small slice? Say dxt. What will be that? It's nothing but the impulse multiplied by, already we know that due to the impulses, what will be the response? It's nothing but impulse multiplied by impulse response function at that time step. So here t is equals to tau c, that means t minus tau. Up to this, it's simple and straightforward. Like if we have a unit impulse of the force value is nothing but the impulse force. So if I want to write down the impulse is nothing but what will be that? Is nothing but the force value f tau and the time interval d tau. Right here it is written. So the what I did here, the general loading I have discretized into small segments, and for one segment if we want to consider the response, dx will be nothing but the impulse at that point multiplied by impulse response function at that point. Okay, so what is the value of impulse? We know impulse is nothing but the value of force f tau. Say for example here the ordinate of force is nothing but f tau, and the duration of time is d tau. So obviously the value of impulse will be f tau multiplied by d tau. This is the impulse multiplied by impulse response function will be the response at t is equals to tau. Clear? Now if I want to formulate the or get the response due to that whole general loading, what I need to do? I just need to integrate the response from 0 to t. Then what I will get? I will get x of t, the total response due to that arbitrary loading. Clear? So to solve this kind of loading, we need to have the concept of the impulse and impulse response functions, because the response due to that impulses is nothing but impulse response functions multiplied by the impulse multiplied by the impulse response functions. Like impulse response functions, we have find it h of t, that means it is the impulse at t. Now h of t minus tau, that means impulse at t is equals to tau. That means you just need to replace the t with t minus tau. That's all in the equation. Now, how to solve it? So this is the complete solution for the arbitrary loading. Only the arbitrary loading. We are considering this only the arbitrary loading. And this is due to what? This response is occurring due to the force itself. And what I said, that the particular integral of this equation, obviously this is a second order non-homogeneous equation of the system ft where the general loading is applied. So obviously it will consist a particular integral part and a complementary part. So obviously the particular integral part will be uh, influenced by the load is acting on this system. So obviously we have derived, okay, due to this general loading what will be the responses. This is the particular integral part, but my final solution will contain the complementary part also, because the damping is present and also the natural conditions are also present. So it's nothing but the damped condition, damped force vibration case. So already you have solved for damped force vibration case. So complementary solution is nothing but e to the power zeta omega nt, a cos omega dt, b sin omega dt. Now, what will be the complete response? Complete response will be nothing but the complementary part due to the initial conditions and the inherent property of the structure, and this is due to the impulse or the general loading part. Now, if so here I have solved for A or B also here, because A and B are the constant over here. So A and B, how we can solve? Using the initial conditions. If we consider that initial velocity is x naught and initial displacement is x dot naught. Okay, here is the important concept, Bob. The x naught is the displacement at time is equals to 0. And what is that x dot naught? Is velocity at t equals to 0. It's not the derivative of the x naught. Okay, don't misunderstood with that. It's the initial velocity. That means v naught. It's the v naught. It's not the first derivative of your x naught. Okay. So if we solve for it, we will get that a is equals to x naught and b is equals to this. So the final solution will look like this: e to the power zeta omega n t x naught, that means the initial displacement cos omega dt. It's look like the force vibration case already we have solved, and the part which actually arise due to the arbitrary loading, and that actually will lead to your steady state response. Now, if the initial conditions, that means okay, I have only 0 initial conditions, that means x0 is 0 and x dot 0 is 0. That means the complete is, the system is starting from the complete rest position. The system is starting from rest, 0 initial conditions. Now if I put the 0 initial condition, what will happen? This part will vanish, right? 0 put here, 0 multiplied by 0, 0 everywhere is 0 there. So only you will live with the part which, that means the particular integral part which actually arises from the force itself. Now here, so the final response, if we have a system which is starting from the rest, that means with 0 initial condition, we have this kind of response where h of t is nothing but the impulse response function. Either it can be impulse response function can be t is equals to that means tau is equals to 0, or tau is equals to for some value. So if we have h of t, that means 1 by m omega d e to the power xi omega nt sin omega nt and all these things. So finally, my particular integral part actually gives me the response of the system. That means x of t, I have forming is nothing but the complete response 0 to t h of t minus tau. Here the impulse response function is taken as t equals to tau, and f tau the value of the force at their d tau. Now, what the Duhamel, now from here we have the concept of the Duhamel integral or the convolution integral. It says that we have a function x of t which is written like that, h of t and f of t. We can write this like x of t is f of t. That means we can convolute the function h of t. We can interchange the function. So that is called the Duhamel integral. So using the concept of Duhamel integral, we will solve different kind of responses under different kind of pulse and step excitations. So from here, like MCQ can come, let a force Ft act on a system, then find out the steady state response. What I say, if we don't have any kind of initial conditions, zero initial conditions, then only this part will give me the steady state response, the particular integral part, which is nothing but the impulse multiplied by impulse response function. So what will be the response xt using Duhamel integral? So either xt can be this f tau ht minus tau dt, or we can convolute it like this, f of t minus tau h of tau d tau, right? So here can be two answers. Now we can easily solve different kind of question using the integral, because now we have the concept or the idea of the impulse response function, and also the idea of the impulses, how we can solve it, and also the value of the impulse response function for different cases. Like here you need to recall these two things. First, if we have the undamped system, that means zeta, for say for example, first we consider the damped system where zeta not equals to 0 and zeta equals to 0. So for this case, the responses will be either the u of t, or you can write it down x of t. So x of t, already you have seen, x of t is nothing but integration 0 to t f tau or p tau multiplied by h t minus tau d tau. Now solve it. H t minus tau is nothing but 1 by m omega d e to the power zeta omega and t minus tau sin omega d t minus tau dt. So you need to remember or recall to solve the problem easily what will be the response of a damped system due to unit impulse. Then only the arbitrary loading or general loading can be easily formed. So this is the part how we can get it. We already have seen the derivation and all these things. And if zeta is equal to 0, the omega d becomes omega n, and that envelope will goes to 0. So only xt will be 1 by m omega n integration 0 to t p tau. Either you can write p tau or f tau. It's nothing but the magnitude of the impulse force at that time. So due to arbitrary loading, now if we have any kind of arbitrary loading, we can solve for the responses using these two equations, using the concept of the impulse response function. So okay, so till now do you have any kind of doubts, or we move to solve different kind of problems?
Yeah, it's okay. What I'm asking is that if it looks more abstract, so if there is any practical applications whilst you're explaining, when you add it, I think it will help us.
Yeah, obviously I will add that applications, like one tower is there and one bus load impact load is coming. Yeah, I will formulate the problems, no problem. Yeah, that will be actually helpful. Yeah, I will solve that kind of problems also, no issue. Just give me the systems, or and I will show you the MATLAB code. I will also the MATLAB code also. They are just, you need to provide the system, you will get the responses. I will show you how to get the responses on using the MATLAB. Any kind of system you can solve here, right?
Okay, thank you.
But you get the concept of the impulse response function, and how to solve different damped and undamped system due to that impulses, right? Straightforward, pretty
Yes,
straightforward. Yeah.
yes.
Okay then. So let's solve one example, like for you system, like here what is the question saying, using Duhamel integral Determine the response of a undamped system to a rectangular pulse force of amplitude P naught and duration Td. Yeah, now you can do it. Now, say for example, Bob, you have a system like this. Say for example, you are doing analysis on some, say for example, you are doing analysis on a water tank, right? So we can model it. It has some mass, and say for example, this actually water tank is subjected to a this kind of forces, arbitrary forces, which is acting at Td duration, and then it vanishes. Now people ask, okay, find out what will be the response. So people will not ask what that generally ask during the examination, but for the real cases, what will ask, okay, if this kind of loading comes, just check and tell me if your structure will be safe or not, right? That kind of problem you, as a structural engineer, you need to solve. Or earthquake load is coming like that here. For the earthquake loading part also, I will show you how to solve for the earthquake loading part using that Duhamel integral also. Earthquake loading is coming. Now tell me what will be the safe limit. So what do we need to do, Bob? You first need to, you have the property mass, stiffness, damping. You can model it. Yeah. Then what you need to do? You need to find out the displacement. What is displacement? It's nothing but the responses. You need to find out the response. What response? Maximum response. So first you need to find out the response due to this load during this time period, and you need to find out the maximum one. Now you check your maximum displacement is within the tolerance limit or not. That's the task. And how we can solve it?
All
Using
right.
the Duhamel integral. Easily, easily. I will just show you how to get it.
Uh,
Yeah, like that. You have a building, you have some earthquake forces coming. Now tell me, what will be the deflection limit, maximum deflection limit, or is it the within the safe limit? What you need to do, you need to find out the responses first, the displacement, the acceleration, the velocity. So we generally deal with the displacement. So you need to find out the xt, you need to find out, look for the maximum st, and then you need to tailor with your different tolerance limits, right? Great. Now, here for the system, look here, the system is not given, only the force is given. You can consider the mass, damping, frequency. Like if we consider this tank, it has a natural frequency. You can find out the omega n. You can find out the mass, all this like of things. Okay, so we have a rectangular pulse force which is acting up to Td. That means during the interval 0 less than equals to t less than equals to Td, we have a force value of P naught, and then the force is vanish. After vanishing the force, obviously the system will vibrate. It will not stop, right? So how to solve it? So E of t, that means few times back I have shown you why I just tell you that recall these things, because when you will code it also, you need that things x of t and u of t is the same. X and u both represents the deflection or the displacement. Okay. Sometimes I use x, sometimes I use u. You can consider any of them. It's just the small u or small x. It's just the displacement. So how we can do it? So we know that the response due to unit impulse of a undamped, look here, the undamped system, that means zeta is equals to 0, is nothing but 1 by m omega n. P of tau is nothing but the value, here p naught is already given, sine omega n t minus tau dt. So for this interval 0 to td, we have p naught value. So instead of p tau, what you need to do, you just put p naught and do the integration. It's a straightforward integration. What you will get finally, you will get u of t is equals to nothing but p naught by k 1 minus cos omega n t. And this response is due to this interval 0 less than equals to t less than equals to td. This is not the complete response. You need to find out the response due to this part also. 0, why 0? So obviously after td, that means when t greater than td, here only you need to, instead of p naught, you replace 0, because I have already The responses due to unit impulses, already I have substituted these things. So here look, so what we will get? The first part 0 to TD, you will have P naught. For the second part, you just put 0 because here no load is acting, but some initial conditions will be there from here, that initial conditions are getting. So some responses will be there. So obviously what the final term will come, if you integrate it, you will get that U of t, your final response, not final response, the response when t greater than td, the response will be this. So the complete response will be nothing but the response this plus this. So this one is, first one is the 0 to td, second one will be greater than td. So few questions may ask from here, like what will be the response during this interval 0 to td, and the options will be given like p naught by k, 1 minus cos omega nt, p naught by k, 1 minus sin omega nt, p naught by k, 1 plus cos omega nt, like that. So obviously this one will be the right answer. Or for your concern, ut, now you can just put these values, or if you numerically solve this using MATLAB, what you will get? You can find out u t is equals to 1 2 3 4 for this entire duration. You found out the u, find out the maximum u, and then tailor with your tolerance limit. That will get you the sense, okay, due to this excitation my structure will be safe or not. Okay, great. Now again we have, like here look, if you have the system, that means your water tank or building, you can get k, you can get omega n, you can solve for it, you will get the numerical values, say 1 mm, 2 mm, 3 mm, whatever it is, I don't know, but you will get the numerical values, you will have some limits as per your code, and then you can tailor with that. I'll show you the MATLAB. That things are actually not done with hand calculations, but in the MATLAB we can easily form it out. So now this question: a system has a impulse response. Like impulse response is given, ht is equals to u t minus 2. Find the system response to an input xt e to the power minus 3t ut. Okay, it's also simple. Like just steps by steps. So impulse response is given, h of t is nothing but u t minus 2. So that means the question should be more elaborative, like h of t is 1 if t greater than 2, then only we will get h of t is equals to u minus 2. That means this phenomena will occur only the value of h of t will be 1 when t greater than equals to 2. So that will be defined. So for now, okay, this is defined. Now input function is given, xt is equals to e to the power minus 3 ut. Now we know the yt is nothing but 0 to t, my impulse response multiplied by the input into d tau. So what you need to do? You just need to solve the integral from t minus 2 to 0, or t minus 2 to 0, or in a way you just need to integrate whatever the limit you have provided. So here we will solve for two cases: one when t greater than equals to 2, and when t less than equals to 2. So obviously you just solve this integral, u is equals to t minus tau, consider it, and when t is equals to 2, that u become t minus 2, when t is equals to tau, it's become 0, and finally you will get yt is equals to, when t greater than 2, it's become 1/3 minus 1 minus e to the power minus 3 t minus 2 by 3, and when less than equals to 0, because there will be no force acting, so 0. So these things actually get done in MATLAB, not done in hand calculations. But these are very simple and straightforward exercise. Like this one, a building is subjected to an arbitrary support motion. Okay, the building is subjected to a arbitrary support motion xt. This is my motion. Okay, the building has a mass 200 kg and damping ratio 0.15. Calculate the response using Duhamel at 4 seconds. So simple kind of, we can apply it also. So the system is also provided. Let's solve it. It's a very good example. But arbitrary support motion. Motion is imparted on the support as a like ground acceleration. That means we need to find out the accelerations. Okay, I will tell you. So mass of the system is given. damping ratio of the system is given. This is the support motion xt, that means this is ft. Okay, the notation is wrong. Input, this is the input, okay, not the response. So obviously damping ratio is provided, that means it's a damped system. So what will be the impulse response function? It's nothing but 1 by m omega d to the power zeta omega nt sin omega dt. Now natural frequency, we can find it out. Say for example, here in the question the natural frequency is not given, kg is given, but if the k is provided, then we can find out the natural frequency, natural cyclic frequency or natural circular frequency. So the natural frequency is not given, so here natural frequency I am considering 10 rad per second, but for your problem obviously the omega n will be provided 10 rad per second, otherwise you cannot solve it. Or the k will be provided. If the k will be provided, you can find out the omega n is nothing but under root of k by m. You can find it in that way. But here that thing is not provided, so I am considering this is that. So omega d I can easily find it out. Omega d is equals to 9.89 for the damping ratio 0.15, because omega d, that means damped natural frequency, is nothing but omega n 1 minus zeta square. Great. Now what I need to do, I need to calculate the response using Duhamel integral at t is equals to 4 seconds. So what the Duhamel integral says, my response yt is nothing but the impulse response functions multiplied by impulse into dt. Now here impulse, why I am writing that down, minus m x t double dot, because just recall when we go through the support motion thing, the effective force comes as this m x double dot, p is equals to m x double dot, because it is excited the ground, the base. So this is nothing but my f tau value. Here xt is provided. What we need to do to get the acceleration? We need to double derivative this with respect to t and multiply it m. Then only we will get this term. So on the next slide, these things have done. Like given input is this, differentiate twice, you will get this. This is nothing but your x double dot, the accelerations. What will be the effective force? F tau is nothing but minus m x double dot t, because the motion is acting on the ground. So this is nothing but the force. Now in the Duhamel integral, y is equals to force, that means you need to calculate, integrate it from 0 to 4, h of 4 minus tau minus m x double dot t. Now just solve for the integral, you will find that at t equals to 4, y is equals to 0.151. Say in the unit, like here it is in kilonewton meter. Here no unit of the excitations are given, so whatever the unit will be, you just need to provide the unit at that things. So for how to solve this type of problems, just I have added this, like any kind of problem can be solved here, pen and paper, but these things can be solved in MATLAB. Like in 4 or 5 line scripts, I can easily solve for it. In the this integral can easily be solved using MATLAB 2 or 3 seconds, right? Or this is a straightforward integral. You can do it also. Like your x double dot t is in a form of sine and cosine terms, so the integral will become easy. Now another question. This question actually given to your assignments, and already these things have been solved by your course instructor. So quickly I will go through the problem statement and try to solve it. So to a tower is idealized as an SDOF system having mass, stiffness, all the parameters are given, subjected to a loading shown in here. The steady state response of the tower at t equals to 4 seconds is given. This is the steady state response at t equals to 0.4 second. Already they have provided the response. Now using the Duhamel integral, calculate a tau and b tau at t is equals to 4 seconds. That means you need to calculate a tau and b tau. Now before going to a tau and b tau, first you need to solve for the steady state response xt due to this load. And your course instructor already have solved this system. Go through that lecture video. I think I forgot the time step, but he already derived the expression for a tau and b tau. So what you need to do, you need to first calculate all the responses due to this loading. So you will get a equation in term of x tau. Then you need to equate this x tau with this x tau, and you will find what is my a tau and b tau. So already, as already derived in the video, I have not added this part. It's a long derivation, but to solve this problem, you need to recall these two things. If this kind of problem come, you need to recall these two parts, a tau or beta, or you need to solve it for the whole system. First you need to solve it up to 2 seconds, then you need to solve it for 4 seconds, then you will get a final solution, then you need to equate it, this equals to this, then you will get eta and beta. So rather you just need to recall these two parts. Now our task is to solve the integral. Here all the parameters are provided, k and m. From the k and m we can find out the natural frequency omega n. Once we get the natural frequency, we have the damping ratio 8%, that means 0.08. So we can find out the damped natural frequency. Once we all have this, we can easily put into this equation. Now, how to solve this integral? This integral can be solved using, these tricks. Like if we have e to the power ax cos bx dx, we have the integral form e to the power ax under root of under a square plus b square cos bx minus tan inverse b by a 0 to t. Look, this and this format similar. So what do you need to do? Replace all the values in eta, solve for the integral. Replace all the value of in beta, solve for the integral. Now f tau value will be 90, because 90 kilonewton. So you need to change according to the system. Like we need to 90 multiplied by 10 to the power 3 to get it into kilonewton. So here I have done the calculations for you, but I insist you should recheck the calculation. So this is the eta value. Now I am putting all these equation, all the values in the equation. E to the power eta we have 8%, omega n we have calculated, t is equals to 0.4 second. Cos omega d already you have calculated, tau 0.4 second. F tau is nothing but this 90 multiplied by 90 kilonewton was there. So 90 multiplied by 10 cube, and we need to integrate it. And the final integration, the results coming as minus 5601 for a tau, and for similarly for beta. Now I have just replaced this one here. Look, just e to the power ax under root of a square plus b square sin inverse b minus this, and this 90,000 I just took common, and for the simplicity of the calculation, and beta comes as this. So I insist like you should go through the integral and check whether the answers I have getting is correct or not. But the way to solve this is this one. You need to recall the expression for eta and beta, and from where this eta and beta is coming, after solving the whole system due to this response. Like here we have solved one system due to this response, like ut is equals to this one, this. So for this also you will get some equation, and where this equation is equated to the equation given in your question, then only you can find eta and beta. Already your course instructor have done it. So we recall the time step. Can you recall the time step, or just you can go through the video lecture, you can get it. Okay, so here I have added one more example. Just go through it, you will find it out. It's simple and straightforward. Every step is written there. Okay, now due to support motion, what I am saying, that due to what will be the impulses or the responses due to support motion. So here xg double dot t is the support motion. So instead of the that force, we have only xg double dot t. When we will solve using the dual integral using the earthquake forces, we will get it right. So here the equation motion is straightforward, mx double dot c xg x dot minus xg, because the xt is the absolute response and xg minus xt is the relative, because that c will experience that relative one, and also k will experience the relative one. So if you solve it, you will get that mx double dot plus cx dot plus kx equals to minus mx dot double dot g. Okay, this one what I just used for to solve the previous example, minus am xg double dot. This is nothing but the effective force. You can like, you can imagine it like your f tau or ft. So if we have any kind of ground motion, we need to formulate the equation of motion like this, and the final solution will be like this, 1 by m omega d, because here I have already substitute the m, so the m part will get cancelled out, and then the rest will be used to solve different kind of responses under different kind of earthquakes using Duhamel integral. So do I first show you the MATLAB portion, or first I will cover that frequency domain part and then we will go to the MATLAB? Because we can solve different kind of problem. Like here xg, we can provide like any kind of acceleration. Say for example, L centro earthquake. If I provide and you just give me a system, I can easily solve it using this equation. Just I will show that part and I will provide that codes also. So first I will show that MATLAB things, or first I will cover up the rest thing. Then I will go for the MATLAB. What do you suggest? Okay, let's say let's quickly go through the first these portions, then we will go to the MATLAB. Now, in frequency domain, like force vibration in frequency domain. Okay, tell me what is the difference between the time domain and frequency domain, or what are these two domains means? Say time, frequency. Say in time domain we have a signal. Say we have a sinusoidal signal of say frequency 2 hertz, or say I can say this is nothing but say 3 sine, this is in hertz, okay, 2 hertz, 2t, this is in hertz. Now if we transform the signal into frequency domain, what we will get, Bob? Here amplitude and here the frequency. What will we get if we do the Fourier transform? What we will get? So if we have a say sinusoidal signal of 2 hertz frequency in time domain, and if we convert it into frequency domain, what will we get, Bob?
Please go ahead.
Yeah,
I'm thinking.
it is like if you have a time domain signal, and it's very important concept for the structural engineer, just focus on it. Like it's very important. Like if I have a signal x of t in time domain, so for example like this, you have a displacement here. For your case, say you have a displacement here, what will be this signal look like in frequency domain, or in frequency domain what we will look for it if the signal is okay or not. So in frequency domain, if I have a signal of 2 hertz sine, so we'll have a peak at 2 hertz only. So this is your frequency ordinate and this is amplitude, so only we have a. If we have a signal which contain different frequency, so if we do the FFT or the Fourier transform, first Fourier transform, we will have the signal. Say if this signal contain two frequency, we will have two distinct peaks at that two things. So if I have a signal, if I convert it into the frequency domain, I can easily get the frequency of the signals. So in time domain, we have the amplitude and time. So in frequency domain, we have amplitude versus frequency. Get it?
Okay.
So if you have a signal like in time domain, what is the frequency? I don't know. Well, I like for a bridge, I have done some testing. Okay, say for example, I have a bridge over there on Brahmaputra River, and I have tested the acceleration, displacement, all these things. But I don't know what will be the mass. Actual mass is there. What is the stiffness? But for if I do the for that signal, if I transform the signal from time domain to frequency domain, what I will get? The frequency component. I can easily identify, okay, the bridge is under these frequencies, or the frequency of the bridge is that, or the frequency of the signal is that. Get my point? Why the frequency domain analysis is very important?
Yeah.
Yeah. So if we have this signal plus say plus we have another sinusoidal signal of 4 hertz, two signal. This is 4 hertz. So obviously, if we convert it into frequency domain, we have a one peak at 2 hertz, one peak at 4 hertz. I'll do the MATLAB examples. Like if you just give me the series, convert it into frequency domain, you will get the frequency response functions. Okay. Now move to that topic, like periodic function. We have already discussed what we know by the periodic function. That means a function which actually repeat itself after certain period of time. Like we have different kind of example, like we have given that example of a machine gun, that the tripod of a machine gun. It can be different kind of loading, but that load will repeat itself after its period. Now if we have this kind of periodic loading, then using the Fourier series, we can express them in the form of sinusoids or sine or cosine functions. So using the Fourier series, we can write any arbitrary periodic loading in terms of the sum of its sinusoids, sum of sine and cosine functions. Sinusoids means the sum of the sine and cosine functions. And the function is actually written as this: f is equals to a naught, which have a static coefficient, plus a1 cos omega 1t, a2 cos omega 2t, dot dot dot, how many harmonics you have until that an cos omega nt. Similarly, we have another coefficient b1, which also follows sin omega 1t, b sin omega nt, and how many harmonics we have. So ultimately, the series or the force ft is nothing but that periodic force. We can write it like that: a naught by 2 plus summation of n equals to 1 to infinity an cos omega nt plus bn sin omega nt, right? Where a naught, a1 and b1 are the coefficients, Fourier coefficients. A naught is the static coefficient, and a1 and b1 are the coefficients related to cos and sine. Now, so ultimately, how we can get the value of an and bn? It's very simple and straightforward. An can be get by 2 by t minus t by 2 to t by 2 ft cos omega t dt, and bn can be found out by 2 by t ft sin omega nt dt. That means if we multiply this equation, both side cos omega nt and sin omega t, and integrate over the period of time, we will get this. Only the cos and sin term will left. And this is very interesting. Like if I show you some phenomena, like if you integrate, just focus on it. If you integrate a sine function or a cos function over its period, what will become it? It will become 0, because this is the positive part, this is the negative part. If you integrate it, that means if you are summing it over the period, it will get 0. So if you are doing some integrations, and if you find that okay, in the integration the sine or cos function is sitting over there, and you need to integrate it over the domain, so obviously it will be 0. Now if we have cos function and sine function multiplied by, and we need to again integrate it over the domain, what you will get? Look, plus plus minus plus, and if you sum them up, you will get 0. So sine function integrate over the period, it will get 0. Cos function integrate over the period, it will get 0. If you multiply cos function with sine function, it will get 0. That means if you have a problem and if you need to solve it, you can easily correlate it. Okay, what will be the answer? Like here the problem, the periodic function is given as a form of like this square function. Find out the Fourier coefficients. That means you need to find out the value of a naught, you need to find out the value of an, and you need to find out the value of bn. So like an is nothing but 0 1 by t 0 to t ft dt. It's nothing but the static component. So ultimately, what we are doing for an, we are integrating the sine function over its period. Obviously it will become 0. That means without seeing it, you can see okay, it can, or it will become 0, or if you perform the integration, you will get also the answer as 0. Now obviously an, how we can get the an, the formula of an, what is the formula of an? Already we have written it here. An is nothing but 2 by t minus t by 2 to t by 2 ft cos omega nt dt. So you need to perform the integration and it will also become 0. So just do the integration step by step. The integration is given. So for n pi, sin n pi, it will become 0. So an also becomes 0, but we will have the bn term, because that term bn is ft sine omega t. So if we integrate it, and we have found out that bn is nothing but, this is simple and straightforward class 12 integrations. Okay, just do the integration. 1 minus cos pi n divided by n pi. This will be n, not r. This it will be n and pi. So the bn value will be, when n will is odd, so we will have this term 1 minus 1, that means 2. It will become 2. That means 2 into 200, 400 by n pi, and if it is even, it will be 0. Okay. Now that was about Fourier series. So using Fourier series, what we do? Tell me. Using the Fourier series, what we do? Using the Fourier series, what we do? We can express any periodic function in terms of sine and cosine. And when we can express it in terms of sine and cosine, it will be easy for us to solve for the responses. Because already we have seen what will be the responses under different kind of harmonic loading. That was the concept of Fourier series. Now Fourier transform, it's a huge part, but I will not get into it, how the Fourier transform thing work, how the derivation is getting. Just I will give you some glimpse of it. Like using the Fourier transform, we can convert any time domain signal into frequency domain signal, or the vice versa. That means if I have a time domain signal, like whatever I have said, like if I have a here, if I have a in time domain, say t and x of t, say this is my sine 5t, say 10 sine 5t. Now I want to, convert it into frequency domain. What I will get? I will get one frequency at 5 hertz. This is my frequency ordinate and this is my amplitude ordinate. So using Fourier transform, we can convert any signal into frequency domain and vice versa. And here, how we can convert it? I just put the pairs. I'm not going to the detailed derivation. If you want the detailed derivation how these transformations are coming, I will share some references. Okay. So xt, if we have xt, I need to convert it into x omega. So xt is nothing but 1 by root twice pi minus infinity to infinity x omega e to the power I omega t dt. And vice versa, x omega response in frequency domain will be 1 by twice pi minus infinity to infinity xt e to the power minus I omega t dt. And we call them Fourier transformation pair. So if I have a time domain signal xt and I want to have a frequency domain x omega, so what I need to do? I just need to put here in these equations. I will have the response in frequency domain, right? If I have a frequency domain signal, I want to convert it into time domain signal. What I need to do? I need to use this expression to convert my frequency domain signal to the time domain signal, and we need to code it into the MATLAB, or inbuilt function of the MATLAB. FFT is there. You can do the FFT like that. So already we have discussed about the power and the energy. Power is nothing but if you integrate for a for the for the for a one time period, we will get the power of a signal, and if we integrate the whole signal with respect to time, we will get the total energy. That means if I have a signal like this, I want to calculate the energy. What I need to do? I need to integrate the square of the signal for the whole domain. If I want to consider the power, so it's a sine so sinusoidal force is there, so obviously it has some period. So during that period, if I integrate it the square of this term, I will get the power of the signal. Now the thing is, I have converted one time domain signal into frequency domain, or vice versa, frequency domain signal into time. How we can say, okay, my transformation is okay? That means whatever the time domain response was, now it is reflecting in the frequency domain. So for this, for the checking purpose, how we can check, okay, whether my transformation is okay or not. For this, one general theorem is there, we call the Parseval's identity. And the Parseval identity says, if you have a signal in time domain, the energy of the signal in time domain and the energy of the signal at the frequency domain will be same. This is called the Parseval's identity. That means if I have a signal in time domain and I have converted it, like I have a random signal, okay, it is coming from some ground excitations and from some structure, and I have converted into frequency domain. So it will contain different kind of frequencies like here, like that frequency, and this is amplitude. This is time versus amplitude. So my transformation is okay or not. How I can find it out? I can find it out using the Parseval's identity. And the Parseval's identity says the energy in the time domain and the energy of the signal in the frequency domain will be same. And energy is nothing but square the signal integrated over the domain, right? We can prove it using the Fourier transform also. So say for example, we have started with the energy in frequency domain, x square dt. Now x, just x multiplied by x, do it like that, xt multiplied by xt. So instead of xt, I am here using the x omega term. Like already we have the pairs, xt is equals to nothing but 1 by root twice pi integration minus infinity to infinity x omega e to the power minus I e to the power plus I omega t d omega. Like here, the transformation pairs are already given. This, instead of xt, I just write this. Now simplify it, you will find out. So what I'm getting, this is nothing but your x omega. So this is x omega. Again, I am doing it for this part. So this is coming as this. So x omega and the complex conjugate of x omega, and that leads to x square omega. That means the Parseval identity says, if you want to check whether your transformation from frequency domain to time domain or time domain to frequency domain is okay or not, what you need to do, you take the signal in time domain, calculate its energy. Again, in the frequency domain, calculates its energy, check whether your Parseval's identity is okay or not. For the random signal, we need to check the identity. For a sinusoidal signal, we know, okay, 5 hertz, we are have the 5 hertz frequency there. But for this signal, where there can be multiple frequencies like this, small, then bigger one, then small, whether my transformation is okay or not, I can find it out. Like if I want to do some FFT of a response of a turbine due to wind loading, I will have different kind of frequencies. Then I need to look for like which one is the dominating frequency, which one was the tower frequency, which one was the blade frequency, which one was the rotational frequency, which one was the wake frequency. Different kind of frequencies can be there. Then we can identify, okay, which frequency we need to look for. And so this is the frequency domain. Now for a spring mass damper system, if we want to calculate the response in frequency domain, how we can do it? So in time domain, we have the equation of motion for it, mx double dot plus cx dot plus ks equals to f of t. Now let's consider if I want to transform it into the frequency domain. So let's consider f of t is equals to as a harmonics, because we will going to use that Fourier transform. So f of t and h x of t, I consider h of omega into e to the power I omega t. Now x of t, differentiate with respect to t, you will get x dot t. Differentiate with respect to double dot t, you will get this. Now after simplifying, what we will get, h omega is equals to nothing but 1 by k minus m omega square plus I c omega, and that h omega is called the frequency response functions. Frequency response functions, FRF. So in frequency domain, my response will be like x of omega in frequency domain, my response will be nothing but the frequency response function h omega multiplied by force in frequency domain f omega. Like in time domain, recall the Duhamel integral. In time domain, the xt is nothing but f tau, that means force in time domain multiplied by the impulse response function in time domain. Likewise, if I want to calculate the response in frequency domain, what I need to do, I need to calculate the frequency response function multiplied by force in frequency domain. So this is the expression for h omega for single dot freedom system, right? Now just you just need to do the derivation part. You will find out, okay, h omega is coming as that. You just need to find out x dot of t. You need to find out x double dot of t. All you need to replace in this equation and solve for h omega. You will find out that h omega is equals to 1 minus k omega c I omega. So what is the relation between h omega and the impulse response function, frequency response function, and impulse response function? It is very straightforward. H omega is nothing but ht, that means that impulse response function at time domain multiplied by the harmonic c to the power minus I omega t into dt. And force in frequency domain f omega is nothing but again ft to the power I omega t. Okay, one more important thing, the Fourier transformation pairs sometimes can be written like this also. In the previous form, what we have seen, that we multiply 1 by twice pi for both the sides, but this formation also correct. For the forward transformation, when we go from the frequent time domain to frequency domain, there will be 1 by 2 pi, and when we divide it back, there will be nothing, because but it's due to the derivation parts only, but that two things will lead to the same conclusions. Okay. And here, how we can get that x omega is equals to h omega and f omega things already. These things have explained by your course instructor. Already I have added this. Just go through it. Okay. Now we will go to the MATLAB part. Okay. That actually give us that sense how we can solve this system using the Duhamel integral under different kind of loading, even of using the earthquake force also, how we can get the responses. So till now, do you have any kind of doubts, or I can go to that MATLAB portion? Okay, well then let's do some exercise in MATLAB. Okay, is my screen visible?
Yes.
Okay. So first, what we will do here, I have added some questions like, for the single love system, I have provided, okay, mass is equals to 25 kg. You can provide different kind of mass also. Stiffness, damping, and subjected to these forcing functions. Okay. Like first one is the uh, that square impulse, then this kind of forces, different kind of forces acting on the system, where f naught is given as the magnitude of the static component is given as 500 kilonewton, and we need to solve for that uh, t is equals to 10 seconds, or I will show how to solve the entire thing. So what we are going to do, we are going to solve this SDOF system. The property of the SDOF system is given: mass, damping and stiffness subjected to these forces. Like first one is F naught, where the interval 0 t to tr, that value will be F naught, and then t greater than tr it will be 0. That means your rectangular pulse. Okay, so how to solve it? So here you can see that it will be a rectangular kind of pulse up to 0 to 1 second. It will be the value of 50, then it will 0. And finally the response will come as that. Now how we can solve it, I will show you in MATLAB. Is the MATLAB interface is showing? Okay.
Yes.
So first what I have defined, the system I have defined: mass, damping, stiffness, and the amplitude of the force. Okay. Then what I need to find out, natural frequency is nothing but square root of k by m. Zeta, that means the damping ratio, c by, only the c is provided. So zeta we need to find it out, the damping ratio, c by twice square root of m by k, the simple equation. The sampling period is provided, ts is 0.001. Now I am considering a time array from 0 to 10 second, because in the question they have said, okay, find out the response at for the 10 second. I can provide it like 100 seconds also, you can make it 100 also, but for the 10 second we will can see. Now I am calculating the omega d. Omega d, that means damp natural frequency. Omega d is nothing but omega n square root of 1 minus zeta square. Now I am defining the first force. This is the first force. Look at the force here. uh, the force value within 0 to tr, the force value, the amplitude of force is F naught, and the F naught value is given 500 kg. And for the t greater than tr, we have only 0. So now I need to define the force here. So look, like when n less than equals to t divided by t minus 1, then it will take the value of F naught, otherwise it will take the value of 0. That means within that interval, the value will be F naught, and rest it will take the 0 value. Okay, so I have defined the force also. Now what I need to do, I need to look for the solution, convolution integral. So I need to define the impulse response function first. So it's a damped system. For the damped system, what is the impulse response function? It is nothing but 1 by m omega d. Look, 1 by m omega d, it is equal zeta omega n t sine omega dt, right? Just recall the expression for that impulse response function for a damped system. Here 1 by m omega d to the power zeta omega nt sine omega dt, or we have written it here also, the responses here, the total response. Okay, so now what I need to do, I have defined the impulse response function, I have defined the force. So what was the final expression in the Duhamel? It's nothing but the impulse response function multiplied by force integrated over the domain. So for this convolution integral, already you can either you can do the convolution easily, that means you can write the code here for the convolution, or in MATLAB it already have the function convolution, conv. If you open this file, open convolution integral, they already did the convolution integral here. How? So we don't need to write down that function file again, we just use the convolution, and convolution between what? Force and the impulse response function. So I can find out the plot for it. So just if I want to run it, what I will get, I will get the response to the rectangular pulse, and the rectangular pulse will look like this. 0 to 500, it have a value 500, then it will drop to 0, right? Now for the second case, similarly, you can do for any kind of cases. Like if I want to, use this forcing function to get this f naught t by t naught, like one kind of ramped function. So how I can do it? First, I need to define the force. So ramp, for the ramped pulse, we can also define, like just comment it, and here the for the ramped one. like this. Within that time interval, I have the value f naught divided by t, and rest I don't have any kind of value. So using this value, this will be the force, this will be the impulse response function. Just run it, you will get the force value and you will get the response also. Yeah. So for this kind of force, this is a ramp kind of force, up and then suddenly fall off, and the response will look like this. So you can add to this script any kind of forces and solve for the response. You can also ramped rectangular pulses, like here whatever I have added four kind of forces. So four kind of forces, for the four kind of forces I have added the solutions. You can easily check whether you are getting this kind of solutions or not, or for your examples also you can check it. So I will upload this file along with this MATLAB code. You can check any kind of arbitrary loading to calculate the responses of a system. So here, like I have defined the system as a MDOF system. You can model your building or bridge or your water tank as a single DOF system, and you can solve using this 2ml integral to get the responses. Get it? Now, if we have the earthquake loading, what will happen? Instead of this ft, if we have the earthquake loading, what will happen? So I will upload this ft part. You get it how I am doing it and how easily it can be solved using the MATLAB within 2 3 seconds, right? So for the earthquake load also, we can define it. Like here is the code for the earthquake. So first I have load the earthquake load, then I define the acceleration, that means force. Like if we go to the earthquake part, so the effective force is nothing but minus mg double dot, right? Minus mg double dot. That means that will be the acceleration to the ground, minus mg double dot, right? So here look at this. I have added the El Centro earthquake. Omega n natural frequency zeta m for mass 1 kg I am considering. You can put any kind of mass. So here I have added the acceleration, and here look at the impulse response function g of x. Similarly, 1 by m omega d into the power zeta omega nt sine omega dt. Right now I need to do the convolution part, and if I run it, I will get the response of this system under the earthquake loading. That means under the earthquake accelerations. So these are the responses. So that was my input, ground acceleration of the El Centro earthquake. This one, the acceleration, I provide the input, solve for the system. I am getting the displacement as this, my displacement of the system, and the acceleration of the system. Displacement will look like this, acceleration will look like this. Now if you want to check it whether your system will be safe against this earthquake loading, what you need to do, you need to find out the maximum displacement. Like here the maximum displacement occur at that tip here, 0.02. Now check with your tolerance deflection, you will get the value of the tolerance limit, and you can tailor it with that. Get my point? How easily these are solved, Bob? You can use for any kind of building. Like if you want any kind of ground acceleration and you want to test it for your structure, say existing structures, you can go it with that. If you want, you just message me. I will share this time histories also, like ground time histories also. You can go with that thing, or you just provide the system. I will solve the system for the ground accelerations. Get it? How
Okay.
easily these things can be solved. Yeah, you can yeah, load any kind of earthquake forces. Instead of here I loaded the El Centro ground motion. You can use different kind of related to your zones, and also this like Kobe, Loma Perita. We have different like Nepal earthquake, Bhuj earthquake. We have different kind of time series. You can check with the time series, and this is very simple. You need to define the force, you need to define the impulse response function, you just need to convolute it. So these are velocity differentiate of c, acceleration double diff of velocity, like this. You can easily calculate and convert it. So I will upload these things also along with your notes, so that you will get the full uh, essence of the Duhamel integral and the time domain approach, right? So do you have any kind of questions? You can ask, or we can, conclude our session. It's like you need
think
to
it's fine.
practice it. Like
Yeah, yeah, yeah.
practice that
It's heavy.
something, yeah, like you need to practice it. It's huge, na. You need to practice is more and more, and particularly what domain. Like I show you how to get the response due to the step and pulse forces. But what we actually need, we need to derive the expression for different kind of loads, like earthquake load. Here I have loaded earthquake load. I can use wheel load. I can use different kind of loads. I need to formulate the impulse response function like that, and I can solve it likewise. Okay.
Okay. I think during our final section,
Yeah.
maybe you need to pick one real life situation,
Yeah, I
one
will. I will.
real life,
I will.
and then you take us to
Yeah.
help us appreciate it very much.
So what do you want? What kind of structure you want to analyze? Just give me. I will just formulate that question. Or just share with me
Can
because
we
I have solved different kind
can
of
we use
problem.
a tower?
Yeah.
Can we use a tower, transmission line tower? Is that
Yeah.
possible?
Tower, building, bridges, any kind of you. If you have the model, okay. Say for example, if you have a building, okay, you have the mass, damping, stiffness properties. Now you can solve it using the Duhamel integral. On the next session, we will see the Newark beta Wilson theta process. Newark beta, very useful method to solve different kind of response in time domain. Newark beta, we have like RK4, Rangagupta 4 method, ODE 4-5 method. We have in the state space format. We can write it and solve it easily. Yeah, yeah, that thing I must do that project thing. Okay, for the real life examples. And if you need it for particular structure, you just give me the structure so I can solve it, or I can generate that code for you also, or we can discuss it over here and we can formulate it.
All
Okay,
right.
then
Thank you.
yeah, Bob, do you want to say something?
Oh, I said thank you. I
Yeah,
appreciate your
yeah, it's
direction.
okay. It's okay. So we haven't time for our that reliability part, but yeah, one day we will resume. Sometimes it
Sure.
is like 5 minutes. Yeah,
Sure.
there is time,
Yeah.
like we have initiated, we will continue it. We are not we are unable to do it right now due to some constraint, but yeah, we will do it. It's easy, man. Like look at this, we can easily solve the structures, we can easily go with that. We just need to know the equations, we need to know the coding part. Things will be easier for us. Okay, then we'll meet on next week. uh, for now, thank you everyone. So I'm leaving the meeting, right?